So let's apply some of what we learned from the earlier chapters and see if we can solve for some different cases. Again, if we look at Newton's third law, we know for every action there's an equal and opposite reaction. Here we see two objects interacting by some general force. Could be a field force. F12 is a force due to 1 on 2. F21 is a force on 1 due to 2. And as we see with the negative sign, these are equal but opposite vectors. Now here, we're looking at a force diagram of the system right here, and we're also looking at a free body diagram. The idea of a free body diagram is to simplify our system such that we're only looking at a single object, and therefore we can calculate what the forces are on it and then see its behavior according to its acceleration. So here we see the floor is pushing on the table is pushing on the floor. There's an action interaction, or action reaction with an interaction. The television is sitting on top of the table, so we have a normal force from the table pushing up on the television. We have the weight of the television pushing down. But if we just want to isolate the television itself and see how the forces are going to behave with it or act on it, we draw it by itself, absent of everything else. I include the force of the table, but I do not include the table itself in the diagram. And clearly we can see with this television, it's at rest, it's obeying Newton's first law. We have the normal force pushing up, an equal and opposite force from the weight pushing down. Essentially it doesn't go anywhere. Free body diagrams, again, are very important for analyzing what the forces are on an object. So therefore, if it's static, like in this case, we can set all the forces equal to 0. If it's an object in motion, then we can set that net force proportional to the mass times the acceleration. So again, we have a few different action-reaction pairs. We have the normal force of the table pushing on the television, the normal force from the television pushing on the table. And here we have the weight of the television pushing down on the table, and the reaction force, which is actually the normal force pushing back up. Now again, whenever we're applying Newton's laws, we have to think about exactly what's happening. If it's in mechanical equilibrium, it's Newton's first law, and we set all the forces equal to 0. If we have a dynamic situation where there's acceleration, then we set the forces equal to, the total forces equal to mass times acceleration. Many times we can actually break the motion into both mechanical equilibrium in one direction and a dynamic situation in another direction. The inclined plane is a great example of this. In the inclined plane, usually the y direction is the direction where the forces add up to be equal to 0, whereas the x direction is where we have acceleration. Now, we have to make some assumptions to simplify the whole thing. First of all, we look at different objects behaving like particles at this point. Essentially, all the forces are going to act on these objects pretty close to their center of mass. Later on we'll talk about torques, but for this case, we're only looking at translational forces. We assume that all masses of strings, ropes, cables are negligible. In the real world they do have an effect, but here we're assuming that they're extremely light compared to the actual force that they can apply. We're only interested in forces that are acting on the object, and as we saw in the previous diagram, we want to neglect all forces that are not involved in changing the motion of the object of interest. So again, looking at ropes, cables, and whatnot, these can apply tension and tension only. The tension only pulls at the end of the rope or the cable. Here we have a free body diagram and a full force diagram of a box being pulled. We've included all the different details here. But again, with the free body diagram, we can just focus on the object of interest. We have weight pulling down here, we have the normal force pulling up, and then we have the tension. These two forces will cancel out in the y direction, and there will only be acceleration in the x direction. And again, here's the box shown where the forces are acting. And again, the tension is the force which is going to create acceleration. So again, free body diagrams, only forces acting directly on the object are included. We don't worry about the forces that the object is placing on other objects, because only the forces acting on the object will tend to change the motion. So again, reaction forces on other objects are not included. As always, with all problems, read the problem at least once. Identify anything that you're given, such as weight, mass, tension, any forces. Draw a picture of the system. Identify the primary object of interest. Usually it's the object that is in motion, but sometimes when we have a statics problem, we've got to see exactly where all the forces come together. Label each force so you know exactly where the force is pushing or pulling. And the direction is very important here. Make sure the force is pointing in the correct direction, because you're going to sort of approximate what you think the motion is going to be, and then check your numbers to make sure that if it's going to move in the, or accelerate in the positive x direction, that your forces, the net force at least, is pointing in that direction. Okay? Draw a free body diagram once you have all the forces identified. Apply Newton's first law if you think all the forces add up to be equal to 0. Apply Newton's second law if there's a net force acting on the object. Solve for the unknowns. And again, if it's in equilibrium, if it's a mechanical equilibrium, if we're satisfying Newton's first law, all the forces add up to be equal to 0. If there's acceleration taking place, then we have the sum of the forces equal mass times acceleration. Now, for a completely stationary object, you actually can get two equations. You can get an equation for the x direction, you can get an equation for the y direction. Here, there's no acceleration in the x direction, there's no acceleration in the y direction. In our two-dimensional world, we don't include the z direction. So, essentially, this object is at rest. We solve for the forces in the x direction, as set equal to 0. Same for y, we can find any unknowns. Here's an example of a statics problem where both the forces in the x direction and y direction are 0. So the first thing I'm going to do is identify where my interest is. I'm interested in this junction right here. We have tension pulling downward in T3, tension pulling upward and to the right with T2, tension pulling to the left and upward, T1, and the only point where all those different forces are going to act is at this junction right here. So, not surprisingly, this is what I'm going to be interested in. Okay? Yes, the traffic light has weight, but we can clearly see the weight that pulls down is simply equal to the tension 3 that's pulling up. That's fairly rudimentary to find out what's going on. So, if this weighs 100 newtons, okay, it's pulling down this cable is going to pull down at this point also at 100 newtons. Again, here's our traffic light, the weight, 100 newtons pulling down, the tension, 100 newtons pulling up. But here's the more interesting system with the blue arrows, where we're looking at the force acting on the junction in the cable. All right. Free body diagram of the traffic light. You didn't have to do this. Again, this is a trivial case. We know with the weight pulling down, there's going to be an opposing force pulling up, because the two forces have to add up to be equal to 0. The interesting case is this case right here, where we have 3 different vectors which all have to add up to be equal to 0. Now again, when you have vectors in the x and y direction, you should really break them to their x and y components. So resolve T1, resolve T2, T3 is pointing in the negative y direction, so you don't have to resolve that. Add x's to x's and y's to y's. So let's do that. We're going to add up all the forces in the x direction, set that equal to 0. Add up all the forces in the y direction, set that equal to 0. Because at this point, we only know what the tension is due to T3. Okay? Look at this. We have two unknowns. We don't know T1. We don't know T2. Okay? How many equations do we have? 1, 2. 2 equations, 2 unknowns. We can solve this system of equations. All right. Let's start with, well, okay, we'll start with this. We know T3 is 100 because if you solve the condition for mechanical equilibrium for the traffic light, T3 has to be pulling up as hard as the weight pulls down. That's easy. We'll go to the junction of the different cables first. Okay. Look at T1. It makes a 37-degree angle with the negative x direction. So I can look at this one of two ways. It's going to have a negative x component and a positive y component. Okay? And I can do the cosine and sine of 37 degrees. Or I can take the supplementary angle for that. Remember, 180 degrees minus the angle gives you the supplementary angle. In this particular case, it'd be 143. And take the cosine and sine of 143 degrees, and that would give me the proper sines. So we resolve this. Again, 37 degrees, we get 0.799, or basically 0.8. X again is negative. Notice it's in the second quadrant. With y, notice that it's positive. Second quadrant, y is positive. And here's my x and my y component. I don't have numbers for them yet. Okay? But what I do is I have a relationship for my first unknown and a relationship for my in the x direction and in the y direction. Do the same thing for T2. I can relate T2x to the total tension T2 and Ty to T2. And basically I add up all the forces in the x direction. T3 has no component in the x direction, just pulls in the y direction. So I'll take T1x and T2x, set them equal to 0, okay? Because again, all the forces in the x direction have to equal 0. T1x plus T2x, T3x is 0, so we don't even add that there. Set them to 0, and now notice I have a T1 and a T2 in this equation. I made my substitution from earlier on. Here's T2x, here's T1x. I'm going to plug that and that into here. And that gives me a relationship between T2 and T1. You know, anytime you do these systems of equations, you want a relationship between the different unknowns. Do the same for the y direction. Now in the y direction, I have T2y pulling up and T1y pulling up and T3 pulling down. So this plus this, notice I've used negative T3. T3y equals negative T3. You can convince yourself because it's pointing downward. I'll substitute this from earlier. Remember, here's what I got. I'm going to substitute that in for T2. Okay? Solve for T1, and I've done my first step. Once you know one of the unknowns, T1, okay, I can take T1 and plug that back up here. Plug that in, I get T2. So again, with this type of problem, classic statics problem, you have two unknowns. I don't know T1, I don't know T2. I know their angles, but I don't know them. And I use the x direction and the y direction to create two different equations to find the two unknowns. Now notice here, I was given this angle and this angle. If I back up, how did I know this was 37 degrees and this one was 53 degrees? You've got to know a little geometry here. There will be many geometry tricks for these different problems. When I look at this diagram right here, I can draw my x-axis through here, and we know this angle is equal to this angle. This angle is equal to this angle. So I took it for granted, but you do have to apply a little geometry in these. I believe they call it interior angles in geometry, but I haven't taken geometry in decades, so I don't remember what they call anything. In any case, here's another statics problem. We have a sled on a hill. The tension of the rope pulls it uphill. We have a contact force, what we call a normal force, which is always perpendicular to the surface, or normal to the surface. And of course, we have the weight. So let's map out all the different forces. One of the forces is known. We know weight. We don't know the normal force. We don't know the tension. Okay. Here is my free body diagram. Notice my weight pulls down. I've angled my coordinate system to match the symmetry of the problem. X now goes in the direction of the tension. The normal force goes in the direction of Y. Thinking about this, we always do this for the inclined plane problem. Why do we do that? Because it aligns different key forces in the direction of the different axes, so you don't have to resolve as many vectors. By tilting this, my normal force and my tension line up with two of the axes. Even though my weight was lined up with the y-axis, now only it needs to be resolved. So, tension will only be in the x direction, normal force will only be in the y direction, because I made this rotation, this transformation, and now I'm going to resolve the weight. Now it makes a 30-degree angle with respect to the y direction, or a 60-degree angle with respect to the x direction. Be careful how you use cosine and sine. Cosine is used when the angle is made with the x-axis for the x direction. Sine is used for the y direction when the angle is with respect to the x-axis. Okay? So when we do this right here, notice I've switched sine and cosine and used 30 degrees. It's probably easier to actually either use the full angle here or use 60 degrees instead. You're still going to get the same thing. So for the x direction, I can use the weight mg, which is 77 newtons, times cosine 60 degrees, which would be the complementary angle, or in this case sine 30 degrees. Again, this requires you to think a little bit about the trigonometry. So I get the x component of the weight, negative 38.5 newtons. See, it's in the third quadrant, so both x and y are going to be negative. I get negative 66.7 newtons in the y direction. Okay? And now I can add x's to x's and y's to y's. And again, this shows an alternative way of determining the angle with respect to the positive x-axis, 240 degrees, using should be cosine with x and sine with y. In any case, in the x direction, we have tension plus the x component of the weight equal to 0. I know what the x component of the weight is. I can solve for tension. That's 38.5 newtons. Okay? The normal force points to the y direction. Fgy is in the negative y direction. So the normal force is 66.7 newtons. Again, here's another example where we resolve the different vectors. Here we have a fire helicopter. It carries 620 kilogram bucket. So you should think right now, that's the mass. Be very careful here. That's the mass. The weight is this times 9.8. At the end of a 20-meter cable, flying back from the fire, at a constant speed of 40 meters per second, the cable makes a 40-degree angle with respect to the vertical. Determine the force exerted by the air resistance. So I have tension pulling up here, I have weight pulling down, and I have the air resistance pushing in the x direction. So there's my free body diagram. Right there is the hardest part of the whole problem. I want to find r. I have the weight if I multiply the mass times the acceleration of gravity, and I can find the tension. I've got two unknowns. I've got an x equation and y equation, so I have two equations. So I resolve the tension component. Here is the tension in the x direction. Here's the tension in the y direction. Notice I'm in the second quadrant, so the x component is negative. I do some of the forces in the y direction, okay? Ty pulling up, the weight pulling down, set them equal to 0, okay? I can then solve for what the tension is, 7,020. And notice here, T sine 60 degrees is the y component of our tension. All right? If I want tension, I then divide both sides by 0.866. There's our mass, there's the acceleration of gravity. Again, there's my tension. Once I have the tension, I can find the resistance force, the air resistance force, because it's pulling in the x direction. The x component of the tension pulls one direction, the resistance pulls in the opposite direction. So these two are equal in magnitude, and we get an air resistance of 3,510 newtons. In the previous cases, I've shown you statics problems. This case right here is a little bit more difficult, because in the previous cases, two of the forces were unknown, and everything else was known, such as the angle and whatnot. In this case, one of the angles is going to be unknown, all right, and one of the forces is going to be unknown. So this is a little bit more challenging, because it's not so straightforward as resolving the x and y components and just setting them equal to 0 and figuring out what is unknown here. All right, here's how we do this. This is similar to the traffic light. We've got a tension going this way, a tension going this way, and a tension going this way. We can resolve this force completely. It's 110 newtons at a 40-degree angle in the second quadrant. The x component's negative, the y component's positive. Okay, so I can get the x and y components there. This force is all y. It's all negative 220 newtons downward. My unknowns are the magnitude of this force and the angle. All right, let's figure this out. The sum of the forces in the x direction equals 0. The sum of the forces in the y direction equals 0. Let's find the forces that we know. I resolve the T1. That's how much tension in the x direction. That's how much tension in the y direction. Now, I have the one force. I have the other force. I need to find the other force in the angle. We know that for the unknown force, T2, the y component is T2 times sine alpha. Okay? So if I do the sum of the force in the y direction, I get T1y plus T2 sine alpha equals 220. Okay? We know what T1y is, so we can plug that in here. So T2 sine alpha equals 150. Okay. That doesn't give me T2, it doesn't give me alpha, because I've got two unknowns in one equation. Let's do the same for the x direction. Here we have T2x. There's only one force component in the x direction here other than T1. I set those two equal to 0, and I get that T2 cosine alpha equals 84.3 newtons. So I'm sort of stuck here, but I'm going to play a trick. Tangent alpha is sine alpha over cosine alpha. I can divide one equation by the other and use tangent to find the unknown. Here's how this works. This equation divided by this equation sets me up right here. Notice T2 cancels out. Okay? I'm left with sine alpha over cosine alpha. Sine alpha over cosine alpha is tangent alpha. Tangent alpha equals 1.78. So I use the inverse tangent to find the angle, 60.7 degrees. Once I know alpha, I can plug this either in this equation or this equation and find the unknown tension. I'll do it for the sine. I find it's 172. So this was more of a challenge. You actually had to use inverse trig functions to go back and find the angle. But in most of these problems, instead of finding an unknown angle, you're looking for two unknown forces.